All right, today we're going to do titration calculations. All right, so you can have a titration. We're going to have three different choices for our titrations. We're going to do strong acid, strong base. We're going to do strong acid and a weak base. We're going to have a weak acid and a strong base. All right, so the one that we did in lab, that was the strong acid, strong base titration. All right, and so we used HCl, we used NaOH, and we got NaCl plus H2O. All right, we did the net ionic last time, and it was H plus OH minus yields H2O. All right, so there are going to be three reactions three reactions that we will write. And when it's a strong acid, strong base, you have H plus and you have OH minus. So strong acid is H plus, strong base is OH minus. Of the three reactions, Ka, Kb, Kw, the only one that has both H plus and OH minus in it is your Kw. So when you write your Kw, you write it the reverse of how it's written there. You write it as H plus and OH minus yields water. No, that's how we wrote it there. The Kw is writing it the other way, H2O. See, I'm just going to reverse it. Is your H plus and your OH minus. All right, so you see that it is the reaction that is reversed. You have to know that when you're starting with water and getting H plus and OH minus, that is your Kw reaction. So of course, if you reverse a reaction, you invert your K value. And so this is 1 over Kw. You can use either reaction. I'm going to stick with always using the Kw as a Kw and not 1 over the Kw. Same with the Ka. I'm going to use the Ka, not the 1 over the Ka. Same with the Kb. All right. Unfortunately, when you are given the question, it's going to say that you added acid to base. And so your strong acid, strong base, so you want to start as reactants. And again, you can do that, but you just need to know that the K value for that is 1 over the Kw. I always have my initials on the right, and I know that something on the right has to be 0. And so I will always have an initial, and then I will have a new initial for any time I'm doing a titration. All right, so let's write all three reactions. So I'm going to write all three reactions, and these are the only three reactions that you will need to do all of these problems. All right, and so you have your HA goes to H plus and A minus. You have your A minus plus H2O goes to HA and OH minus. And then the one that we just did was H2O. That goes to H plus and OH minus. It doesn't matter what order you put your products in. All right, so this is your Ka, always small. This is your Kb, always small. And this is your Kw, always very small, always the same. 1 times 10 to the minus 14. All right, so your Ka, you will have to look up a Ka value or a Kb value. And note, when you add those two up, your Ka and your Kb, you get Kw. The A minus is canceled, the HA is canceled, and you get your Kw. And of course, when you add reactions, you multiply the K values. And so we also know that that Kw is your Ka times your Kb. So if you're given a Ka and you need the Kb for the conjugate base, you simply take the Kw and divide by your Ka if you want the Kb, divide by your Kb if you want the Ka. So if you have one of them, you can easily get the other. All right, so we're going to do a problem that is part of a titration problem. All right, so we're going to do parts of the titration, and then we're going to put it all together and do an entire titration. All right, so this problem is calculate the pH when 15 mils of 0.1 molar NaOH has been added to 25 mils of 0.1 molar HCl. Oh, I think we already did this one. Did we do this one? 25 mils of 0.1 molar HCl. I remember doing this one, but all right, we'll do it again. Why not? All right, so this is a problem where you are doing a titration of NaOH, which you have to recognize as a strong base. So that's your OH minus. And a strong acid that you have to recognize, HCl, is a strong acid. And so you have your OH minus and your H plus. You have your three reactions. There's only one that has both of those in it, and that is your KW. And so you write H2O goes to your H plus and your OH minus. Now we have to get our concentrations. And so we're going to have an initial. And since we have both H plus and OH minus, we're going to have a new initial. All right, to get your concentration, it is not 0.1 and 0.1. It was 0.1 before you added them together. 15 mils of 0.1 molar NaOH was added to 25 mils of 0.1 molar HCl. And so they have been mixed. Now you have a final volume of 40 milliliters. And so you got to do MV is equal to MV for your H plus. You got to do MV is equal to MV for your OH minus. So anytime you're mixing two liquids, you got to get the new concentrations. So your HCl was 25 mils of 0.1 molar. So 0.1, 25 mils. I want to know what is my concentration now that the volume is 40. I added 15 to 25, and my volume is 40. All right. And since my units are both in milliliters, and they must be the same units, it doesn't matter what those units are, but they must be the same. You simply divide both sides by the 40 mils, divide both sides by the 40 mils, and the milliliters here cancel the milliliters there. All right, and so your molarity for your H plus when you push the buttons, 0.0625 molar. And you'll notice that I'm going to use more sig figs than I would normally use. Everything's 2, you should give 2. I'm going to give 2 for my final answer, but my intermediate answers, I always keep more sig figs. All right, and so I'm going to do the same thing for the OH minus. We started with 15 mils of 0.1 molar. So 0.1 molar, 15 mils. What's the new molarity now that we've mixed them together? And it is 40. All right, so you divide both sides by 40 again, and you get your concentration of your OH minus to be 0.0375. All right, so now we plug it into our initial. So we plug those two numbers into our initial. All right, so our H plus, 0.0625, our OH minus, 0.0375. All right, and so here, and then water is a liquid, so it doesn't matter. You always have to have at least one thing 0 on the right. Whether you're writing the Ka, the Kb, the Kw, all of those numbers are small. You will always have one or both of those numbers be 0. When they are not 0, then it's going to go to the left until one of them is 0. And so that is then your limiting reagent, the one that you're going to run out of, the smaller amount. In this case, it's the OH minus. So we subtract our 0.0375, we subtract our 0.0375, and we add our 0.0375, but since that's a liquid, we can ignore that. When it is a Ka or a Kb and you've got an Ha or an A minus, you cannot ignore that, but when it is making a liquid, we can ignore that. All right, and so now my OH minus is 0, and when I do that subtraction, I get a 0.025 for my H plus concentration. All right. And if you do your initial concentration, like 0.025 in the KW is so small here, it's 10 to the minus 14, you never will change the value. So you don't have 0. It's got to come to the right. So it is plus X. It is plus X. All right. But this X value is extremely small. It will never change the initial concentration. All right. Unless the initial concentration is 0, because you can't have 0. It's going to be a very small number. And so since it said calculate the pH and this 0.025 molar plus an extremely tiny number, which will not change it, that is simply go to your pH. Your pH is the negative log of the 0.025 molar of your H plus. And so your pH is equal to 1.60. All right. So that would be if you are doing a titration and you didn't add enough of your base yet. You would have to add more base until you hit the equivalence point. The equivalence point of a strong acid, strong base is a pH of 7. All right, so that would be a part of a titration. What's the pH after you added so much, didn't hit the equivalence point? In this case, it would be the answer pH of 1.6. All right, so here is one of the harder questions, and that is going to be calculate the pH at the equivalence point when 25 mils of 0.1 molar HF is titrated with 0.15 molar NaOH. All right, so we have 3 reactions that we can choose from, and we must pick the right reaction. All right, so you have to recognize HF as a weak acid. You have to recognize NaOH as a strong base. You also have to recognize that Na plus never has anything to do with anything. It is always a spectator ion. And so what you have is you have OH minus and you have HF. There's only one reaction that has an OH minus and a weak acid, and that is your Kb. All right, so if you go back up and look at the 3, if you had OH minus and H plus, then that's the Kw. But this is not H plus, this is a weak acid. All right, and so when you have a weak acid with a strong base, all right, and then I'm going to write it in the correct order, and that is always with the strong acid or strong base as a product. All right, so that's going to give you water, and that's going to give you your F minus, so that is one of the 3. This is your Kb. So it's very important to write down what the equation is that you're writing. And so this reaction is the Kb reaction. All right, so for the equivalence point, you have an equation, all right, which is completely different. It might look the same. You might think it's the same. It is not the same. Your titration equation is mv over c for your acid is equal to mv over c for your base. All right, if you're doing mv is equal to mv, which we did before, that is acid on one side and acid on the other side. And then you would do mv is equal to mv, base on one side, base on the other side. That is not a titration, that is a dilution. This is a titration, acid on the left, base on the right. molarity, volume, and coefficient for your acid, molarity, volume, and coefficient of your base. All right, and so this is going to determine what amount of NaOH, what volume of NaOH is going to be required to reach the equivalence point. Because we have everything else. The molarity of our acid is given. It is 0.1. The volume of the HF is given. We use 25 mils. The coefficient, we wrote the KB reaction, the coefficient for our HF is 1. The molarity of the base was listed as 0.15 molar. The volume of the base, well, we don't know. That is the question. We are at the equivalence point. So what volume was required to reach the equivalence point? And then your coefficient for your NaOH, also a 1. All right, so to solve it, you simply divide both sides by the 0.15 molar, and you get 16.6 repeating of your NaOH. Again, I don't round numbers when I'm doing this until I am finished at the end. Then I give the sig figs. I carry all my numbers along with me. All right, and when it says the equivalence point, what that means is at the equivalence point, your HF concentration is going to be exactly the same as your OH minus concentration, and then both of them will go to 0. All right, so now we need to know what is that concentration that they both have. And so you have to do MV is equal to MV. MV is equal to MV. This is for your HF, and this is for your OH minus, and we know those numbers must be exactly the same. All right, so your HF, we had a 0.10 molar. We used 25 mils of that. Now I want the molarity. Now that my volume is the 25 mils plus the 16.6 repeating, which is a 41.6 repeating. All right, and so I will get my number there, and then the same thing for my OH minus. It is 0.15. The volume of that was my calculated 16.6 repeating. What is the molarity now that my total volume is 41.6 repeating? If you round that to 2 sig figs and use 42, use 17 for the mils, that's fine. I'm not going to take off for that, but those numbers that you get must be exactly the same. If they are not the same, then you need to use more sig figs. So this is 0.060, and this is 0.060. And so the molarities, by the definition of the problem that says you're at equilibrium, that defines that they are both exactly the same and they are both going to 0. So if you are rounding numbers and you're not getting the same number, then don't round your numbers until the very end. All right, so it's going to go, all right, so we'll rewrite the reaction again since we can't see it anymore. All right, so we have our, here was our HF. Here is our OH minus, and that is in equilibrium with H2O and the F minus. So we have the same number, 0.060 molar, 0.060 molar. That is our initial. We didn't have any of our F minus. Water is not included because it is a liquid. All right, and so it's got to go to the left until one, or in this case, both of them go to 0. All right, and so they are both the same number, and so they are both going to go to 0. So minus 0.060 minus 0.060 at the equivalence point. They are equivalent. They both go to 0. And now this side is a plus 0.060 molar. All right. So now the question becomes, calculate the pH of 0.060 molar of F minus. And this is the KB reaction. All right, and what was given was the Ka for HF is 6.7 times 10 to the minus 4. So the Ka for HF is given, F minus is not listed in the Kb chart, and so we don't need that to be listed because we know how to find the Kb once we have the Ka. So the Kb is the Kw divided by your Ka. So you take your 1 times 10 to the minus 14 and then divide by the Ka that you either find on the chart or is given in the problem, which is 6.7 times 10 to the minus 4. And when you push the buttons, you get a Kb value equal to 1.5 times 10 to the minus 11. All right, so that is an extremely small K value. All right, and so you don't have to worry about checking your X value. Your initial 0.06, so if you want to do that, you have your CB over KB. Well, that is much greater than 1,000. It's a billion, all right, because your KB is so small. All right, so all that means is we do not have to check our answer for X. So we go minus X plus X plus X. We have 0.060 minus X, X, and X. And so X squared over 0.060 minus X is equal to the Kb. Make sure you know what reaction you're getting your values from. This is the Kb, not the Ka. You use the 1.5 times 10 to the minus 11. If you use your Ka, you're going to get the wrong answer. All right, so you neglect your X, and you have your 1.5 times 10 to the minus 11 times 0.06, and then you take the square root of that, and you get your 9.5 times 10 to the minus 7. All right, so then again, X could be whatever X is. Is it H plus? Is it OH minus? Is it neither one? You have to know what X is. So X in this problem is your OH minus. All right, and so you're going to take the POH, get that by taking the negative log of the concentration of OH minus. So you take the negative log of that number, and that gives you a 6.02 as a POH. And then we know that our POH plus our pH equals 14. And so that is a 7.98 pH. All right, so that is a very difficult problem. So when you have an equivalence point, you got to find out what the concentrations are of the two products, your strong base and your weak acid. Both of them are going to go to 0, but then you have to find the pH. So some very small amount, 10 to the minus 7, very small amount, comes back to the right, and then we can find our POH, and from that we get our pH. All right, so there's a lot of steps to that simple looking problem. We had to get a KB from a Ka. Lots of different things had to happen to answer that one question. All right, let's try. On this one, let's calculate the pH at the half equivalence point. All right, so this is a very interesting question. All right, so we want to calculate the pH at the half equivalence point. All right, so we just calculated the equivalence point. The equivalence point took 16.6 repeating milliliters. So the half equivalence point is when it is 8.3 mils repeating. All right, so the half equivalence point, so we're halfway there. 16.6 repeating is required to get to the equivalence point. Halfway there is 8.3 mils. All right, and so we want to calculate the pH. All right, and again here, you want to make sure you're using all the numbers on your calculator. we have the same exact reaction. All right, so we have our H, we have our, let's see, we have our, this side, our HF reacting with our OH minus. All right, in equilibrium, we got our H2O, and we got our F minus, so we have the HF and our OH minus. So we have to calculate our new concentrations. All right, so we have to do MV is equal to MV again. So here is MV is equal to MV for our HF. Here's our MV is equal to MV. This is for the half equivalence point. And so our volume of our NaOH that we added at the half equivalence point is 8.3 milliliters. And so when we calculate that, all right, we have our HF, we had our 0.1 molar, we had our 25 mils. Is that right? Check. We had our 0.1 molar, 25 mils. That is correct. All right. And now that we've added 8.3 mils, now we're at 33.3 repeating. And what's the molarity of that? And so for the NaOH, to get to the half equivalence point, our 0.15 molar, we had to add 8.3 repeating milliliters. What's the molarity now that it is 33.3 repeating milliliters? Of course, we're adding the HF, which has the 25 mils, and we've added 8.3 mils repeating, and so that's where the 33.3 repeating mils is. All right, so we added some NaOH. So you take your 0.1 times 25, 0.1 times 25, and then divide by your 33.3 repeating, and that gives you a 0.075. Then you take your 0.15 times your 8.3 repeating and divide by your 33.3 repeating, and that gives you a 0.0375. All right, so I'm going to put that into the same decimals because I know that one of the things on the left is going to go to 0. We haven't reached the equivalence point. We're at the halfway there. We didn't add enough OH minus. That's the one that's going to 0. That's the lower number. So we subtract 0.0375. We subtract 0.0375. We add 0.0375. Make sure to remember to add the 0.0375. So now what we have is we have 0 OH minus. We have 0.0375 molar of my HF, and I also have 0.0375 molar of my F minus. All right, so once you have added some of the base and you are not to the equivalence point, you have a buffer. So if we are doing this titration and we're adding volume of NaOH, our pH is going to be going up. All right, and so here is the equivalence point. That is your equivalence point. All right, so that's the volume at the equivalence point. Here's the pH at the equivalence point. All of these things before the equivalence point is a buffer. All right, so this is your buffer zone. So anytime you are not to the equilibrium point, like the half equilibrium point, you are a buffer. And so because what do you have? You have a concentration of your weak base. It is 0.0375. You have a concentration of your weak acid. What is it? 0.0375. And you have zeros for any H plus or OH minus. And so once you recognize you have a buffer, you simply have pH is equal to pKa plus the log of A minus over HA. And what is extremely interesting, anytime you have the half equivalence point, whatever you had for HF, your OH minus will be exactly half of that, which means now you're going to have exactly the same amount of HA and A minus. And so that gives you that the pH is equal to the pKa plus the log of 0.0375 divided by 0.0375. Every time you're at the half equivalence point, those are exactly the same, and the log of 1 is 0. And so if you get a question that says, what is the pH at the half equivalence point? That is the easiest question on the test, because every single time that is the question, the answer is the pKa. So all you have to do is find the pKa. Since the Ka is given, Ka is 6.7 times 10 to the minus 4. All right, so then you get the pKa. That is simply the negative log of your Ka. And the negative log of that is 3.17. So your pH at the half equivalence point is 3.17. All right, so that was a lot of work to get to the pH at the half equivalence point. So if you don't remember that the pH is equal to the pKa at the half equivalence point, you can do that half hour of work and get the answer. But it will work that way every single time. You never have to do it again. Your pH is equal to the pKa at the half equivalence point. All right, let's try. Let's try this one. All right, calculate pH. All right, we're going to do initial. We're going to do after 20 mils. HCl added. At the equivalence point. Half equivalence point. And then after 70 mils, HCl added. All right, so there's part A, there's part B, there's part C, there's part D, there's part E. Oh, and then graph it. Graph. All right, so we're going to get all of our pHs, all of our volumes, and then we're going to graph this titration curve. All right, so we're getting the initial after 20, after okay, so I didn't give the actual thing. So when 35 mils of 0.2 molar NH3 is titrated with 0.12 molar HCl. With 0.12 molar HCl. All right, so now again, you have three reactions that you will need. And we're going to need, well, actually, we're going to need all three, but we're actually not going to write the KW. But in all of these problems that have multiple questions, you're going to need both the Ka and the Kb reactions. All right, so initial, so let's draw what we're doing here. We have a titration going on, and in our Erlenmeyer flask, we have our NH3. All right, so here we have our NH3, 35 mils of 0.2 molar, and then in a burette, we're going to slowly add our HCl until we get our color change, and we know that we are at the end point. All right, so the initial pH is, well, what's the pH of the NH3? So the part A is calculate the pH of 0.20 molar NH3. All right, so you do have to recognize that NH3 is a weak base. And so we are writing the base reaction. So NH3 plus H2O goes to NH4 plus and OH minus. So you need to know that NH3 is a weak base. And so we have to look up the Kb value for NH3. And when you look up the Kb value for NH3, you find it to be 1.8 times 10 to the minus 5. All right, and so here we do our 0.2, 0, and 0. All right, so we didn't start the titration yet. We don't have two things. We just have one thing, the NH3, 0.2 molar. All right, and so that is on the left, and both of the ones on the right are 0, but it's going to go to the right a small amount. And so you have 0.20 minus x, you have x, and you have x, and you have x squared over 0.20 minus x is equal to 1.8 times 10 to the minus 5. Now, to check to see if we have to put in the x value to successive approximations, you got to take your initial concentration of your base, divide by the equilibrium constant for the base, Kb, and see if that is greater than 1,000. So you take 0.2 divided by 1.8 times 10 to the minus 5. All right, so when you take that, you get 11,111. So 11,000, whatever. Anyway, so it is greater than 1,000. So you neglect x, you don't have to check it. All right, and so we can just eliminate the minus x because our value is greater than 1,000. And so we get 1.8 times 10 to the minus 5 times 0.2, and then we take the square root of that, and we get 1.9 times 10 to the minus 3. So we get 1.9 times 10 to the minus 3. 1.9 times 10 to the minus 3. So your x value is 1.9 times 10 to the minus 3. All right, so then you have to recognize that that number is your concentration of OH minus. And so now we're going to get a POH and then convert that to a pH. So your POH is equal to the negative log of your 1.9 times 10 to the minus 3. And that is a 2.72. And then you subtract from 14 to get your pH of 11.28. All right, so your weak base has a pH of 11.28. All right, well, let's find the pH of the 0.12 molar HCl. Remember, HCl is a strong acid, and so you can get rid of the Cl minus. It has nothing to do with it. And so that is simply, what is the pH of 0.12 H plus? And so pH is equal to the negative log of 0.12. So strong acid, strong base is very simple to get the pHs of them because their concentration, 100% ionized, so we could write that. You got your HCl of 0.12 goes to H plus and Cl minus, 100% ionizes. This is now 0. This is 0.12. This is 0.12. So I'm losing the sound. All right, and so you have the negative log of 0.12. And that is a 0.92 for your pH. All right, so if you stuck a pH probe into the HCl, it is 0.92. If you stick a pH probe into your NH3, it is 11.28. All right, so now we're going to add the 20 mils of HCl. So part B, we're adding, so we still have our 35 mils of the 0.2 molar NH3. And to that, we're going to add 20 mils of our 0.12 molar HCl. And we want to know what the pH is. All right, so you have to find, again, the correct reaction. So again, you have three of them. You want the one that has the H plus, right? Because that's what HCl is. That's the strong acid. And it has the weak base. Generic for a weak base is A minus. And that, of course, is the Ka reaction, right? And so you can write generic, you can write specific. I'll write it specific. I want the Ka reaction. So when I see this, I know that I have to have the Ka reaction. So NH4 plus goes to H plus and NH3. All right, and so I have a concentration of my H plus. I find that by MV is equal to MV. I have a concentration of my NH3. I find that by MV is equal to MV. I know one of those is going to go to zero. So it's going to go to the left until one of the things on the right are zero. They both go to zero if you're at the equivalence point. All right, so your H plus, it said you have 0.12 molar. All right, 0.12 molar. You added 20 mils. What is the molarity now that the volume is 55? We add them together. The total is 55. We had a 0.2 molar at a volume of 35. What is the molarity now that the volume is 55? All right, so you just divide both of those by 55. So 0.12 times 20 divided by 55. And that is a 0.0436. And then the 36 keeps repeating. So, all right, and then you take your 0.2 times your 35 divided by your 55, and you get 0.127 with the, this is 0.127 with the 27 that keeps repeating. All right, and so, and then this NH4 plus is 0. So you see that the 0.0436 repeating is smaller than the 0.127. And so we subtract 0.0436, we subtract 0.0436, and that gives one of them to be 0, and the other one has a number. All right, and so we subtract it on that side. It is forming it on the other side, plus 0.0436, repeating. So we have 0.0436, and we subtract our 0.04, and we get our 0.0836, repeating. All right, and then the H plus is 0. So now we are prior to our equivalence point because the H plus is at 0. And so since your H plus is at 0, you have a concentration of your weak acid and a concentration of your weak base. Now you have a buffer. And once you recognize that as a buffer, you put it into the Henderson-Hasselbalch equation, where pH is equal to the pKa plus the log of A minus over HA. All right, so this right here tells you, so this is your initial, and this is what I call the new initial. So you have an initial, and then you'll have a new initial. Not equilibrium, because you have a 0. You have an initial, that's going to react completely till something on the right is 0. Sometimes both things are 0. Once you hit that, now you know you have an initial concentration on a reactant side, initial concentration on a product side. The X value does not have to be checked. You can do it by equilibrium. But if you know it is a buffer, you simply put it into the buffer equation. Except we don't have a Ka. We have a Kb. So to find Ka, we have to take Kw and divide by the Kb. So the Ka is 1 times 10 to the minus 14 divided by the given Kb of 1.8 times 10 to the minus 5. Yeah. And so that is a 5.6 That is, what the heck is happening here? All right, go away, you stupid thing. Okay. All right, so then we have our 5.6 times 10 to the minus 9 minus 10. All right, so that's your Ka. All right, and so then you take the negative log of that to get your pKa. All right, so the negative log of that is a 9.26. All right, so the pKa is 9.26. All right, so we have the 9.26 plus the log. A minus is your NH3.08. 36 repeating, and then your HA is your NH4, which is your 0.0436 repeating. And that gives you a 9.54. All right. So this problem on the test is going to be worth a lot of points because it's going to take forever to finish. All right, and we will continue there next time.